Welcome to Neutron Networking Demystified. I am Shalu George, and my co-presenter today is Naveen Joy. Many people find networking in general to be quite intimidating, and that has a lot to do with a lack of exposure and familiarity. To make matters worse, networking and cloud in general tend to use a lot of jargon and many acronyms. My attempt through this session is to elucidate cloud networking and to make it accessible to all. Hence, the term demystified in the title. I have been involved with OpenStack since the Portland Summit in 2013. My work has involved writing code in Python and Django for the Horizon dashboard. Over the years, I have come across people from many diverse backgrounds now involved in OpenStack. I myself have a master's degree in molecular biology. This only speaks to the very welcoming and inclusive nature of the OpenStack community. But this makes it all the more important for us to understand the subject matter and explain it as simply as possible to others. That would open the doors to many more. And as we know, more people means more solutions. So let's move on. Let's first look at the history of networking in OpenStack. So when OpenStack started out in the very first release of OpenStack, which was the Austin release in 2010, the networking functionality was actually hard-coded into the compute service, Nova. This, of course, made it really hard to independently evolve the compute and networking features. However, by the fulsome release in 2012, a new networking service was introduced, and this service was called as Quantum. The name of the networking service was changed from Quantum to Neutron as part of the Havana release in 2013. This name change was due to a trademark conflict with a manufacturer of backup systems. So with the introduction of Neutron, networking became modular and could be evolved independently. Okay, so now let us begin by looking at what Neutron is. Neutron is a networking as a service project in OpenStack. Neutron has a server component that is found running on the controller node. Neutron also includes a set of APIs, plugins, a SQL database, and authentication software. In addition to that, Neutron also has several distributed programs that are running on various other nodes. So Neutron in general enables network devices and technologies to work together in an infrastructure as an environment, a service environment. So this diagram gives us a very high-level view of how the OpenStack Neutron networking service works. As I mentioned earlier on, Neutron has two software components, a server component found running on the controller node and various distributed plugin agent programs running on the compute and network nodes. The Neutron server also includes an API server, and as you can see in the diagram, you have an ML2 plugin, which has its own API extensions and different types of drivers. So we will be looking at the various components of this diagram as we proceed. So let's begin by talking about the Neutron API server. The Neutron API server is what enables users to interact with the Neutron server. So a client can make a RESTful API request to the Neutron server using one of three means. A user can type in a command in the OpenStack CLI client or command line interface. A user could click on a button that says, for instance, Create Network on the Horizon dashboard. Or alternatively, one could make use of an app created using the OpenStack Software Development Toolkit. The RESTful API requests are used to perform CRUD operations on various network resources. Now, what are these network resources? Network resources could include networks, ports, subnets, firewalls, routers, and security groups. So the RESTful API actually uses an HTTP post, get, put, or delete request to carry out CRUD operations on the network resources. The CRUD operations and their HTTP equivalents are shown here. Create is the same as post, read is the same as get, update is the same as put, and delete is the same in both CRUD and HTTP. Now we look at how things were before the ML2 plugin was introduced. Neutron, before the ML2 plugin, had a monolithic plugin structure. What this means is that a separate plugin was required for each and every type of network device. And as one would guess, this made the plugin not very user-friendly or modular. It was also not possible to simultaneously support multiple networking devices. This is how things looked after the ML2 plugin. So you can see all the ORs, which now changed to ANDs. ML2 stands for Modular Layer 2 Plugin. So as the name suggests, it made the plugin both modular and reusable. The plugin now acts more like a framework. It made it possible to use multiple networking devices simultaneously, and as a result, it reduced the amount of effort involved in development and maintenance. Let's take a more detailed look at the ML2 plugin. The ML2 uses a single plugin, multiple driver architecture model. ML2 makes both network types and network devices pluggable using drivers. So how would one plug in a driver? To plug in a driver, ML2 provides driver APIs. A vendor or an operator can use their own driver APIs to develop their own drivers. ML2 provides two types of drivers. You have network type drivers and mechanism drivers. First, let's look at network type drivers. The network type drivers allow a tenant to build a particular type of network for their project. A network type driver could be used to build both a project network or a provider network. We will be talking about both those types of networks as we proceed. A variety of networks are supported by the network type drivers. You can have a VLAN, a VXLAN, a GRE, or a flat network. Mechanism drivers, on the other hand, allow vendors to integrate their own specific devices or mechanisms. Out of the box, ML2 supports two open source mechanisms, which are Open vSwitch and Linux Bridge. And ML2 allows multiple mechanism drivers to be used simultaneously in a network, so which makes it very useful in a real-world data center which has many devices from many vendors being used. An example of a mechanism driver for ML2 is Networking VPP. So this is a look again at the Neutron server. So what you can see, this is basically a summation of everything I spoke about. You have the user or the client interacting in three different ways with the Neutron API server. The Neutron server includes the ML2 plugin and its API extensions and the two types of drivers, the network type drivers and the mechanism drivers. So the whole idea behind the network type drivers is that the network type code is completely separated out and doesn't have to be repeated. This gets rid of a lot of redundancy. So I've been talking about nodes. So what is a node after all? A node is nothing but a server. It can be physical, that is bare metal, or virtual, on which various OpenStack services are run. Some of the types of nodes that are important as far as networking is concerned are the controller node, the network node, and the compute node. You also can have a storage node and a dashboard node. In an active standby configuration, you will have a redundant controller and network nodes. So what is the controller node? The controller node is the node that runs all of OpenStack's API services, be it Nova, Neutron, Keystone, Glance, Cinder, Swift, Heat, and so on. All their API services run on the controller node. Any API request for any service first comes to the controller node. As one would guess, the Neutron server is part of this controller node. The Neutron server is nothing more than a Python process that serves Neutron RESTful APIs. So this picture shows us the controller node. It has, as you can see, API servers for all of OpenStack's services. It performs instance scheduling, and it also stores the state of resources using the SQL database. It runs an AMQP, which is an advanced message queuing protocol. In this case, it is RabbitMQ. It's a message broker service that is used to reliably send and receive messages between the various service components running on other nodes. So how is a request received by the Neutron server, and what steps are involved in its fulfillment? The Neutron server first authenticates a request by sending it to the Keystone Server API process, which is again running at the controller node. Once the request is validated, it is sent to the Neutron server's ML2 plugin. The ML2 plugin, firstly, saves the request in a SQL database so it can keep track of the status of the request. The ML2 network type drivers are then responsible for handling the network type details, like allocating a VLAN ID or a VXLAN ID for network segmentation. The ML2 mechanism drivers then utilize a queue to send a message to the corresponding plugin agents running at the compute and network nodes. Each mechanism driver has a corresponding plugin agent running at the compute and network nodes. And it is these plugin agents that consume the request and fulfill it. An example of a request could be the binding of a port to a virtual machine on the compute node. So this gives us an overview of the Neutron server architecture, again summing whatever I described. You have the Neutron server with its Neutron API and its extensions, the ML2 plugin with its own extensions, the SQL database where all the requests are stored, and the queue, which is used for interacting with the distributed plugin agents on various nodes. So how do the mechanism drivers actually provision the network? They communicate asynchronously via a message queue and provision the underlying physical and virtual network infrastructure. So let's move on to talking about another very important node, which is the network node. What a network node does is that it provides connections between different networks in a project and between a project network and an external network, such as the internet. A router namespace or a virtual router is attached to the network node, and that enables connection to an external network. We will be looking at network namespaces and virtual routers further on. A network node also provides two VMs, DHCP services, which is configuration services. DHCP stands for Dynamic Host Configuration Protocol, and metadata services as well to VMs. So here we have a look at the network node. The network node provides layer 3 routing, floating IP, DHCP, and metadata services. The virtual router that we find running at the network node acts as a gateway to an external network and connects instances attached to project networks at the compute nodes. And for layer 2 connectivity, you have the ML2 Plugin Agents running at this node. The data network. The data network is the network that provides a connection between the compute nodes and the network node. The data network is the network that is used by the various VMs in a project to firstly communicate with each other and to communicate with an external network. All the communication between the VMs on different networks or a VM and an external network goes through the data network to a router, of the virtual router that I spoke about, attached to the network node. So this diagram puts together the network and compute nodes, and it shows how the data network connects the two. The topology of the data network depends on the type of ML2 driver used. So we move on to talking now about the management network. The management network is used by an ML2 mechanism driver to communicate with its corresponding plugin agents that are running at the compute and network nodes. The management network is used for all of OpenStack's internal communications. And as a result, the projects have no access to this network. The management network connects the controller, network, compute, and dashboard nodes. So this diagram shows us a Neutron production deployment. It has a redundant controller and network nodes and several compute nodes. The compute nodes are the hypervisors in which the Nova instances are spawned. The ML2 plugin agent provides layer 2 connectivity, and the API network, which is something I didn't speak about, is used for serving all of OpenStack's service APIs to clients. Every OpenStack production deployment also has an external network, which is used for providing floating IPs and external network connectivity to all project instances. So now we come to talking about what a project network is. A project network is a network that can be created and managed in a self-service manner by a non-privileged user, that is, a user that is not an administrator. Project networks are importantly virtual networks, and they are created on the vSwitches of a compute node. Project networks also provide configuration, that is DHCP and metadata services using the network node. In the case of most project networks or self-service networks, the type of network used is VXLAN or Virtual Extensible LAN. And the reason is that VXLAN can support many more networks than VLAN, and VXLANs are also entirely virtual, making use of overlays. What overlays are and overlay networking is something that we will look at as we proceed. Overlay networking. So examples of an overlay network are VXLAN, as I mentioned, and also GRE. What overlay does is it involves the encapsulation of a regular L2 frame with a VXLAN header. The packet is sent to the destination host using a VXLAN tunnel. This tunnel is set up over an existing IP network, which is called as the underlay. VXLANs are preferred because they provide better network stability as compared to VLANs, and they make use of layer 3 routing. So what is a provider network? A provider network, as opposed to a project network, must be created and managed by a network administrator. When a provider network is shared by an administrator, a project user can then go ahead and attach their own instances to it and can view that network. Provider networks differ from project networks in that they need actual physical configuration of the hardware in the data center. A provider network is essentially created by mapping the network's segmentation ID to an existing network in the data center using what is known as VLAN tagging, that is 802.1q. So it is the physical routers in the data center that provide both floating IP functions and layer 3 routing. So this is what the whole picture looks like. Here you have two project networks that are then connected to a virtual router at the network node, and this in turn connects via the provider network to physical routers in the data center. Now we move on to looking at certain networking concepts and how they apply in Neutron. Subnets are a block of IP addresses that are assigned to a network. Private IP address ranges are used. The subnet is represented using the CIDR notation, that is the IP address, a slash followed by the mask. This is an example of a CIDR notation. You have the IP address. The first 3 octets represent the network, and the last octet represents the host, and you have the mask following it. A project user assigns a subnet to their network, and the management of these IP addresses is done by the Neutron server. IPAM service is IP address management. Overlapping subnets can be used by different projects. Port. What is a port? A port is nothing but a connection point in a network to which a single device can be attached. A port, again, can be both physical or virtual. A physical port would be a port on a physical switch, or you can have a virtual port like a vSwitch. Ports are created just like any other network resource. And here are some attributes of ports. You can have network, that tells you the network that the port belongs to, the MAC address of the port, the device owner of the port, the security group that the port belongs to, the project of the device owner, and the fixed IP address of this port. Floating IPs. We've been talking a lot about floating IPs. What are these? Floating IPs are another service provided by Neutron. Floating IPs are temporary IPs, and they are public-facing and are used or enable external communication. Floating IPs are assigned by Neutron from a pool of available IPs in the external network. The admin is responsible for setting this pool of floating IPs. A user can associate a floating IP with their instance. For example, a floating IP can be set for a port on an instance. Network namespaces. So it's network namespaces that make virtual routers possible. To implement a virtual router, Neutron makes use of Linux namespaces at the network node. Project users can create their own virtual router. Each virtual router that is created by a tenant is isolated from others by a namespace. Namespaces, as a result, allow each tenant router to have a different set of network interfaces. Namespaces also make it possible to have overlapping IP addresses amongst different tenants. So this is what the picture would look like. You have two project networks here that connect to a virtual router that is made possible through a network namespace. The virtual router then connects to a physical router in the data center. The router provides SNAT, that is Secure Network Address Translation. The virtual project router connects to the physical router in the data center, as you can see. So we move on to talking about security groups. A security group is a collection of ingress and egress permit rules to filter traffic going to and coming from an instance. So what they do is essentially act like a virtual firewall for an instance. In OpenStack, the security groups are applied to a port. Security groups, importantly, can only contain permit rules. There are no deny rules. That is, if something isn't explicitly permitted, it is essentially denied. Security groups are also stateless, which means that reverse rules are not required to permit response traffic. The order in which these rules are inserted doesn't really matter. Port security. So port security allows you to enable or disable security at the port level. In OpenStack, by default, port security will be enabled. When initially a default security group is applied to a port, and it only enables all IP communication between instances that are attached to the very same security group. Port security can be disabled in some cases. For example, if the port you're talking about is nothing but a virtual machine which represents a networking device. Lastly, we talk about allowed address pairs. So by default, you have a fixed security group port security set on a port, which will only allow traffic from a particular IP MAC address pair that is known to Neutron. Ports have an attribute which is called as an allowed address pair attribute, which allows you to add additional IP MAC address pairs. Traffic from these IP MAC address pairs can then pass through the port. So here you have a port, and by default, traffic from a fixed IP MAC address can pass through this port. In addition to that, you can have additional IP MAC address pairs that are specified as part of the allowed address attribute, and then that traffic would be permitted as well. All other traffic is blocked. Now, when we talk about allowed pairs, it can be an IP MAC address pair, or it can be a subnet or a CIDR MAC address pair. So here are some further learning resources. If you happen to be new, not just to Neutron, but also to OpenStack, these are some courses that can be accessed via the website of the online learning portal Udemy. There is a coupon code, OS_Sydney, which is exclusively available for OpenStack Sydney attendees. So with this, we move on to the last segment of our session. Naveen will now be talking about troubleshooting a Neutron deployment.
Thank you, Shalu. So I will talk to you guys about troubleshooting Neutron networking from my practical experience. So first starting point to troubleshoot Neutron networking is looking at the log files generated by the Neutron server and the Neutron agent. You can also turn on debug equals true in the Neutron's configuration file, and that will generate a lot of logs, and you can understand the detailed inner workings of Neutron and all the calls that it makes. So assuming that you don't have a log analytics engine, a simple way to look through the logs is to search for traces or errors. That's the first thing that I use to troubleshoot in my deployment is to grep for traces or errors in the server.log, which is the log file generated by the Neutron server, or the agent.log on the various compute nodes. Another piece to see is where do you exactly, if you have so many compute nodes, which compute node would you actually troubleshoot? How do you isolate the problem? Isolating the problem to a compute node or to the controller node is the first step towards troubleshooting. So you exactly know where to look at. Neutron port show output, if you do that, the output will tell you there is a field called binding host ID. What that field says is it shows the host name, the compute node name on which that port is bound. That is the host that Nova scheduler has scheduled that VM on and has told Neutron to bind a port on. And it should have a valid value of that host. If for some reason binding has failed, you will find binding failed over there, and then you can go directly onto that host where the scheduling has to happen, and then you can start troubleshooting there that something wrong has happened. So you will have to check with the Nova logs as well to say where has Nova scheduler told Neutron to bind a port and why has it failed. Then the next step is to check the status of all of the agents using, you can use this command if you don't have it integrated into your Horizon dashboard, OpenStack Network Agent List. What that will show you is it will show you the node, the name of the node, and all the agents running on that node. In the network node, you should see the layer 2 plugin agent, the metadata agent, the DHCP, and the layer 3 agent. All of these agents are required for layer 3, the network node, and the networking services to work. On the compute node, you should see the layer 2 plugin agent as up. Then if you have issues with VMs booting up or SSHing into a VM after it has booted up because cloud init failed for some reason, you can check the OpenStack console log show of the instance. You can provide the instance name or UUID, and it will show you whether the instance received an IP address via DHCP and whether the cloud init process, which is responsible for configuring the instance as it's booting up, that is at runtime, whether that was successful. Did it get the SSH keys correctly from the metadata server? So you can see all of that from this console log, and then you can infer that, okay, those pieces are all working fine, whether they are working fine or not. Now be aware of the default security group rules, because I've seen some of my customers spending a lot of time troubleshooting basic problems related to security groups. So you have VMs in 2 different networks attached to the same router. The VMs can ping their gateway, but not each other. So what's going on? Is the gateway not routing? Everything was working fine, but the fact was that the security group blocked ingress ICMP traffic. So that's the default behavior. So if you can't ping VMs between networks, then first point to look at is, do you have an ingress ICMP permit rule? Then you can also go onto the network node, and then look at the QRouter namespace, QRouter or QDHCP, and then ping the virtual machines from there. So you can use this command here, that is, you're executing this command directly in the namespace, because this is required. You can't ping a virtual machine directly from the node itself. You have to go into the namespace, and this ping should be successful in most cases, because the security group is configured by default to allow the IP address of the network node from where you're pinging. The namespace IP address is allowed.
Excuse me, so that needs to be running, that command needs to be run on the network node?
Yes, that's where the namespace is.
Right, okay.
So you will have to go onto the network node where the namespace resides and run it. Yes. Yeah. So finally, TCP dump.
I just want to clarify that's in the case that you're using legacy routers. If you're using DVR, you probably have to run this in the computer.
Yeah, we are not even going to the DVRs, because that's another dimension of complexity is what I've realized, deploying and running DVRs. But yes, if you are using DVRs, yes, that's a different situation there. The final thing is that TCP dump traffic on the network node where you suspect an issue. So this will tell you whether the virtual router is receiving traffic, whether the DHCP is sending its offer, and whether it is receiving an acknowledgement from the virtual machine. You can do that. What I have done is, I've also, if you really want to dump traffic on a virtual switch, you can create a virtual Ethernet pair, which is basically a virtual patch cable. Attach one end to the vSwitch and the other end to the namespace on the host, and then dump traffic on the host. So in that way, you can just take all the traffic coming in from that virtual switch, dump it on that host, and then you can open it and view the traffic and see whether there is a problem. Finally, you can use TCP dump on the router DHCP namespaces as well to see whether the VM is able to ping the router or whether the DHCP packets are flowing through. Using the -E option will show the actual MAC addresses, so you can check for your VLAN IDs, are they correct, VXLAN IDs, and so on. So that concludes our presentation. Thank you. If you have any questions, we are here to take your questions at this point. Yes?
Are there any recommended practices in deploying the management network in terms of IP addressing, bandwidth, and designating to have the case of devices?
When you're looking at the management network, right, you will have to make sure that it is locked down, that management network, to only the devices that are under the administrator's control. For instance, you will have to have an isolated IP address, like a private IP for that management, and only the controller node and all the agents, it's for management communication. Only they should be able to communicate. None of the tenant VMs should have access into that management network. It's completely locked down, and probably in your company, if you have a management network from which you are managing, you are running commands, SSHing into the nodes, only permit those to access the management network. Performance standpoint, there is nothing much. It can be a very basic network, right? Because it's just for management communication. It's not the data network. That's where you will have to look at how do you improve the performance of the virtual machines. Are you really using techniques like SRIOV or directly attaching NICs, and all of those techniques directly go into the data network, right? And the management network is restricted for management communications, basically the message queuing and communication between the controller to the agents. Any other questions? Okay. All right. Thank you, everyone.
Thank you.